Okay, so let's look at handout 11A. I have to say that 11A is really exciting to me. This is really at the core of what goes on in analytical finance all the time. So we're going to be doing in this chapter, in this handout, evaluation of projects using our discounted cash flow methods or DCF methods or models. So let's jump right in. The DCF methods, the great thing about them, as I've indicated before, is that we can use them to evaluate any project. And all we have to do is consider its time normalized cash flows. And what I mean by its time normalized cash flows are simply the present value of its cash flows and the riskiness of the project, which, as we saw in chapter 10, we want to measure in our discount rate and our cash flows. And remember, we have those four risks that we always want to consider. We have duration risk, risk-free risk, and then we have an increment for market or industry risk, and we have project-specific risk. So when we talk about DCF methods, we're usually talking about three primary methods, and these are the net present value method, the benefit cost ratio, which is also sometimes called the profitability index. I will consistently call it the benefit cost ratio, and the internal rate of return method. For all of these methods, we want to be careful to always evaluate one project at a time for one participant at a time. Don't get two projects involved and don't get more than one participant involved in our evaluation. And with our DCF methods, we're going to consider only cash inflows and outflows to and from this project for this participant. So if there's the mother of all big piles of cash in the project and it stays in the project, it doesn't flow out to anyone, we don't consider it. We're only considering inflows and outflows of cash and only to and from the participant's view that we're taking on. And now, happily, we can use a proper sign convention for all of our cash flows in our equations and on cash flow diagrams. So no more of this common sense. We know the PV total has got to be negative in this case because it's an outflow, et cetera, et cetera. For every stinking cash flow for every project, assign it a proper algebraic sign. And then finally, we're going to evaluate all our cash flows at t equals 0. This is what I mean by normalizing them back to t equals 0, because then they're all on an apples to apples basis, and we can do things like add them together and make ratios out of them and stuff like that. So our key assumptions are going to be, for right now, let's look at a participant who's considering independent projects and a participant who has an unlimited budget. Additionally, we're going to have to include all the marketplace and investor assumptions and implications we've already covered. I had a big slide with a whole mess of assumptions we had to consider. So just remember there's a lot of other assumptions in our models too. And later in the next chapter, we'll look at an alternate set of assumptions here. We'll look at mutually exclusive projects instead of independent projects. And we'll look at having a limited budget, or what's called in finance capital rationing. So let's start with, we're going to walk through our three methods here. Let's start with the NPV method. And to do that, we need to have our definition of net present value. And net present value is just the sum of the individually present valued cash flows for this project, for this participant, including every stinking cash flow, anything paid or received at any time. So first, what we're going to do is for each cash flow that she hopes to get, she has to put out as a cost in the beginning of the project. We're going to present value each one of those individually, and then we're going to add them up, and that's called the net present value of the project for that participant. So we can write this mathematically, and here's our NPV equation. And it looks very much like our PV tote equation that we had in chapter 8b. The difference here being now is that we're going I is equal to, instead of from 1 for that first future cash flow, I equals 0 to number of cash flows. So this ensures that we capture any cash flow at t equals 0. T sub I is still going to be the time of cash flow I, and CFI is going to be our project risk adjusted cash flow I. So very similar to our PV tote equation, but we're just moving our index start point to 0 to make sure we capture every stinking cash flow. And now, of course, also we're using a proper algebraic sign convention here. So there are two important properties of the NPV formula. The first is that the net present value of opportunity cost investments is equal to 0. And I showed you how that worked in the notes for chapter 11, handout 11. And second is, if we find mission fitting investments, we're looking around, we're looking for projects. If we find one with an NPV that's greater than 0, we should do it, because if we don't do that, we put our money in our opportunity cost investment, we get an NPV of 0. If we find something better, we get an NPV of more than 0. That's going to make us wealthier. So this leads us to our rule for applying the NPV formula. We're going to invest in a potential project we're considering if the NPV is greater than 0. And if it's less than or equal to 0, we're not. And what are we going to do with that money? We're going to put it instead into our opportunity cost investment. Nothing wrong with that. That's a good thing to do. Okay, so there are also two important interpretations of the net present value. We looked in the notes at an example where the net present value of a project was $4.76. So I'll continue with that here. So the first interpretation that's important, and we use this all the time, is called the increased wealth concept. And it says that positive NPV projects increase the investor's wealth by the amount of the NPV. So in this case, where the NPV was $4.76, we would say, if we go ahead with that project, if we make this investment, we've just made the firm richer by $4.76. And I showed you how that actually does work. It's true, it's true, it's really true in the lecture for handout 11. Okay, but there are some caveats on this. Richer is not measured against doing nothing. It's measured against putting the money we had for the project into our opportunity cost investment instead, not against doing nothing. Okay, so specifically what I mean is, if we didn't make the investment in this project, we would have put the cash into our opportunity cost investment and enjoyed an NPV of 0. Second important concept is called the equivalence concept, and that says investing in our positive NPV project is completely equivalent to receiving its NPV today. And again, in the lecture for handout 11a, I went over showing you how that is true. Honestly, the increased wealth concept is the one that we use more, so it's important that you understand that one. Okay, so let's move on. Our second DCF evaluation method is the benefit cost ratio, and this is a ratio, just like we had in our ratio analysis chapter. So the benefit cost ratio is defined to be, in the numerator, the present value of all the positive cash flows for this participant for this project, divided by the absolute value of the cash outflows. So these would be the negative cash flows, okay? And PV, of course, means we've discounted them all first. And what are we discounting by? We're always discounting by, with these methods, our opportunity cost of capital that we got from our opportunity cost investment. So as always, first present value each cash flow, then add them up. Never, ever, ever add up your cash flows without present valuing them first when you're using DCF methods. Okay, so the BCR method is not quite as good as the NPV method because it doesn't say how much wealthier a project will make us. That's why we think of it as sort of a bang for our buck ratio, but it's more important to know how much wealthier a project is going to make us, and BCR does not help us with that. And our third and final, for us, discounted cash flow evaluation method, we looked at the internal rate of return method, or the IRR method. So first we had to define what we meant by an internal rate of return. And an internal rate of return is just the discount rate or the interest rate that makes the NPV of a project equal to 0, okay? And mathematically, how are we gonna make that work? We're just gonna go back to our NPV equation, and we're just going to set it to 0. So over here, we have on this side exactly the NPV equation as we first developed it, except instead of putting our opportunity cost of capital in here, interest rate, discount rate, in here, we put in the internal rate of return, and now we solve this for the IRR. So how are we going to use this method? Well, as always, same with all DCF methods, we want to establish our opportunity cost of capital and all our cash flows, and then we'll solve for the IRR using these cash flows. And now we're going to compare the internal rate of return to our opportunity cost of capital. If the internal rate of return is greater than our opportunity cost of capital, what that means is our cash is going to be growing faster than our opportunity cost of capital rate of growth, so we should go ahead. On the other hand, if our internal rate of return is less than our opportunity cost of capital, what it means is that our cash would be growing in this project at a slower rate than it would be growing in our opportunity cost investment. So we don't want to go ahead. We'd want to put our cash into our opportunity cost investment instead. So the IRR method has a couple of problems. It has problem number one, which is same as the BCR method. Okay, it does not tell us how much wealthier a given project is going to make us. Okay, same as BCR, but it's got another problem, which is actually much bigger. And that's that when we're solving this, this means always when we're solving something like this equals 0, we're finding the roots of a polynomial or a real equation. And as I showed in the lecture, for complicated examples, we might have a complex number solution for the roots, and we might get a bunch of roots, and we don't know which one is correct. And neither NPV nor BCR have this problem. So we would say, in the quants in finance would say these are more robust methods than the IRR method. However, we have some good news here. Math to the rescue. People way much smarter than me have found that the IRR method is guaranteed to work for 4 types of projects. Something like this where you have a negative cash flow only at t equals 0, all the other cash flows are positive, or if you flipped this thing over the x-axis and you would have one positive cash flow here and all the rest negative. Or on the other hand, if we have all negative cash flows here and one positive one at the end, or we could flip this over the x-axis and we'd have all positive cash flows instead of one and then one negative one at the very end. For these 4 cases, the 2 that are shown and the 2 additional we get by flipping these over the x-axis, the mathematicians have shown that the correct IRR is the smallest real positive root of the polynomial equation, or the real equation. The IRR method is not guaranteed to work for projects like this, where you may have a positive or negative cash flow at any old time. So the good news is that projects like bond projects, for example, are perfect for the IRR method because they always look something like this. And usually they have a bunch of uniform cash flows and then one big blobby cash flow at the very end. Or they might look something like this. So these are the IRR method is great for bond projects, and the yield to maturity is the IRR for the project by the bond, evaluating with non-risk adjusted cash flows. And also, the IRR is very appropriate for loans, where we saw for mortgage loans, we typically get a big blob of money in return for making a uniform payment back for 3 years or 30 years, whatever it is. So IRR is used for projects like these all the time. It works just fine for them. Okay, so now in terms of you solving IRR problems in homeworks and on exams and things like that. So for a 2 cash flow project, you can always find the IRR with algebra and a calculator, right? You just go back to the FV is equal to PV times, you know the story, 1 plus R. We could say IRR raised to the T, something like that, and you can do the algebra and solve for the IRR. Okay, if we have a 3 cash flow project where cash flow 1 occurs at t equal 1, cash flow 2 occurs at t equal 2, and cash flow 0, of course, happens at t equals 0, we can find the IRR with the quadratic equation. So for a 3 cash flow project, where the cash flows happen at integer times, like end of year 1, end of year 2, not end of year 1.5, end of year 2.7, or time 2.7. If we have something like that, we'll get an equation that looks like this, and we can multiply both sides by 1 plus IRR squared. And that's going to give us, when we do that, an equation that looks like this. And all of us hopefully will recognize this as something we were tortured with in high school or grammar school, depending on your education. This is our classic find the roots of a quadratic equation, a parabolic equation, and this is exactly, this up here is exactly of this form, 0 equals ax squared plus bx plus c, where in our case, x is equal to 1 plus IRR, a is equal to CF0, b equals CF1, c equals CF2, and then IRR equals x minus 1. So we can solve this using the quadratic equation, and I did an example showing how to do this, I think, in one of the example practice problems. Okay, and I think that is it for this handout 11A. So once again, I'll bid you adieu and look forward to speaking to you again soon.